Check. Cool. All right. How's everyone doing? Cool. So my name is Sugu. I'm going to be the track host for this afternoon. I'd like to introduce this session by Stephan and David. They are from 1&1 Mail and Media. They are going to talk about how to integrate Kubernetes with legacy systems using Service Mesh. And without further ado, here's Stephan and David.
Thanks.
Hi, everybody. Do you hear me? OK. Hi, everybody. Wow, that's quite a crowd. As far as we could see from SCET, about 600-something people would like to come. Or, of course, some of them just have 2 or 3 in parallel. But it's quite a crowd, and still people are coming in. But we have a tight schedule, so let's get started. We have some seats left here, and the middle seat in the first row is still free. So everybody who would like to volunteer? OK. So this talk is about Service Mesh loves legacy, likes legacy, Service Mesh and legacy, versus legacy, maybe hates legacy. We will see in the talk. What we did at 1&1 is we have a freshly new Kubernetes cluster, and of course we have a bunch of legacy services. And what we'll see in this talk is how we tried to merge both worlds by using Service Mesh technology, and how good we did or how bad we did. So who are we? My name is Stephan Fudeus. I'm an expert for container platforms. I have a 16 years track record of distributed systems. I work in 1&1 Mail and Media since 2017, and I'm with the 1&1 group since 2005. My current main job is being a product owner for our internal Kubernetes cluster, so a set of clusters we just use for internal purposes, where our application operation teams are running their applications on.
OK, I'm Meder-Marouelli. I'm a systems architect with 1&1 Mail and Media. Originally, I started as a physicist and gradually moved through HPC to the internet business. And that shift occurred like 15 years ago. And for a couple of years, I'm a systems architect with the focus on everything connected with automation. So that's a lot of work at the interface between standardizing software development and creating the matching infrastructure together with people like Stephan. So to give you a quick idea of who we are and what we do, United Internet is one of the biggest German internet providers and specialists. Actually, we have something like over 9,000 employees at a time, close to 100,000 servers and 10 data centers distributed worldwide. So there's quite a number of challenges. 2 main business units. Applications is essentially what you'd call web hosting, and the mail, email, and online data storage business. And access would be mobile phones and landlines. So our business unit is the 1&1 Mail and Media. As you can see, we are offering mainly email services with about close to 36 million active users currently. Most of them using free accounts, but there's premium services as well. You see the logos of a couple of brands. You may or may not have seen them. GMX and Web.de being the largest ones in Germany, and Mail.com also being available internationally. As I mentioned, that's the product portfolio that Mail and Media is offering. Main thing, obviously, everything around email, contacts, calendar, stuff like that. We also have an online office offering, so that's sort of similar to what you know from Google, probably. And we also offer cloud storage. Think of Dropbox or Google Drive. So how do we get these products to our customers? So this is the architect's view, as simple as it can be. So Our product guys have the product ideas, obviously. Developers turn that into code, which is stored somewhere in GitLab, together with the configuration for the applications. From there, we have a build system. Let's think Jenkins or GitLab CI, which produces the deployable artifacts, which are stored in a repository like Artifactory from JFrog. And we also store the configurations together with the artifacts there. We picked the artifacts up with a tool for deploying. We are using GoCD for orchestrating things like that. Under the hood, we are doing great amount of things using Ansible, which is a good thing because with Ansible we can deploy to the host-based world. About 15,000 hosts, which we currently have in Mail and Media. On the other hand, we can use Helm from Ansible to deploy into Kubernetes. So you see both hosts and Kubernetes. On front of that, we have a load balancer distributing the load between them, or also between the data centers to provide the products to our customers.
So that's about the context in which we are living and working. And when we started Kubernetes, we of course had a strategy why we want to do containers. And you see parts of them there. We provide Kubernetes as a central installation for the application operations teams, and we use that for centrally providing orchestration of containers within the one-on-one Mail and Media. The main goal we want to achieve is having fast deployment cycles. We want to enable the application development and application operating teams to fastly deploy their new changes, their customer demands to a running infrastructure. And as well, developing new products. And previously, before we had Kubernetes as a platform, of course, we partially used virtualization. We used bare metal as well, depending on the requirements. And every time a team had a new product idea, first new systems had to be set up. New Puppet code had to be written. And with Kubernetes, that's just easy. You have your already running infrastructure. The capacity is already there. You just throw your deployments into the cluster, and everything works just out of the box. We have a focus for multi-tenancy. So this is why at least we try taking part in the multi-tenancy working group of Kubernetes as well, because multi-tenancy is crucial for us because we cannot provide a Kubernetes cluster for every application operations teams or even every development team for their own stuff. We provide central clusters. It's about 15 clusters so far with overall like 500 servers. And in these clusters, we provide each tenant, each application operations teams their space. And we separate them from each other, of course, by using RBAC and pod security policies. Our benefit is we have friendly users, so we don't need to have strong multi-tenancy requirements. It is sufficient to just have them their space where they cannot break the others. Of course, as nearly everybody who is going for Kubernetes, we focus on microservices. We do not try to do lift and shift of the existing monoliths, but we try to make small services and then put them into Kubernetes. As said, we have multiple clusters and we split them on multiple dimensions. We have a split between front-end and back-end networks, and only the front-end networks, of course, are exposed to the public internet. We have multiple data centers where our clusters are running in. In fact, that's 3 clusters, 1 in the US and 2 in Europe. We have a split according to live and non-live systems. And interesting is we do not use virtualization for running Kubernetes clusters because since we have a central infrastructure provisioning, we said, hey, that we don't need that additional layer. We can really just use the full power of bare metal. Another thing which gets important when we talk about service mesh later is our network infrastructure. In our clusters for the pod siders and the service siders, we use non-routable IP addresses. So they are not routable outside of the Kubernetes clusters. And they are reused. We use the CG-NAT space from RFC 6598. And so the pod siders within different clusters are overlapping. So they cannot be uniquely addressed. That's important, as we will see later.
Okay, it's nice to have containers, but the company is in business for like 30 years, and that resulted in about 1,000 services and applications being online today. As you can imagine, most of them still are running on VMs or hardware, and currently about 10% run on the Kubernetes cluster. On top of that, 1,000 applications, as you can probably imagine, not all of them are microservices yet, so it's getting worse with microservice transformation. That's generating a pretty messy mesh of dependencies, which needs to be handled some way or the other. On top of that, it's obvious we probably will not be able to move all of them into Kubernetes and containers, because many are not yet cloud native or cloud ready, so some are just not stateless, need some storage and stuff like that, which we cannot easily currently provide in the Kubernetes world. We have some very funny legacy things in the ACL area where we use IP addresses, fixed IP address lists and stuff like that. So all of that needs to be sort of translated into the cloud native world, or at least these two worlds need to interact for quite a substantially long time. And we'll see how our approach looks like for achieving that. And there's another thing I'd like to mention. A typical application may look like that. So Java is the main programming language in 1.1. Spring Boot, the current standard, good old Spring we had before, but we also have PHP, we have a little bit of JavaScript and Node.js, stuff like that, and a bunch of other things. But on sort of all applications, you'd like to have a number of services for observability, for telemetry, for a lot of things. So besides your actual application code, an entire stack of libraries usually are used in these applications. Not all of them might be in all applications, but that's how it could look like. So every request traverses a number of layers which are baked into the applications before it can leave the application, and when entering the next call dependency, it traverses that stack back. So this is some implementation effort, and this is a substantial duplication of work. And so wouldn't it be nice to have something that looks like that, which removes all these layers which you need in all the applications from the applications themselves and puts them into infrastructure components, like using a proxy which is handling that, totally language agnostic, totally platform agnostic, and so reduces that duplication and lets the developers focus on the functionality of their application.
So that's where the benefits of the service mesh come into play. The main goal of the service mesh is to deal with the service mess of microservices, because if you gather additional microservices, it gets 100, it gets 1,000, and it gets thousands, and you need to keep track what you have there and how they behave. You need to have observability. We heard that term quite a bit the last 2 days. What service meshes are doing is they externalize required standard functionality, like extracting telemetry out of the services, routing of requests, doing A/B switching, blue-green deployments, canary deployments. They help us with doing circuit breaking. So if your upstream service has a problem and is down, then it just cuts the circuit. Especially important if your upstream service just gets slow. You don't want to have a slow application yourself, so you cut the application off, and then you can work just with having no data. Of course, circuit breaking does only work properly if your application is aware of that it's optional and it's just not there at the moment and can behave accordingly by using cache data, for example. Rate limiting is always an interesting thing when you especially know that your service can cope with a specific amount of load and you want to you want to take care of the point in time where you get too many requests, but you still want to serve those you know you support. If you don't do rate limiting, it might be that your service breaks down completely, and then you have nothing anymore. And the most important thing for a service mesh for us was doing encryption on the transport layer and having authentication and authorization. And especially, we will see that in a few slides, that's especially important for us when connecting Kubernetes services with host-based or legacy services. Another benefit of the service mesh is that they can be configured in a declarative way. So no change to the applications themselves. I can just declare some YAML stuff, and we will see an example in a second. I can just declare a bit of YAML and then have my application enriched by that functionality. I can maintain them in a central fashion. I can do infrastructure as code. I have all my configuration just in a central Git repository, and I do every change there. I roll that out, and I have everything there. And one other prime feature of a service mesh is that it's language agnostic. We just saw the slide where we had an exemplary Java stack of applications, but of course, usually you don't have homogeneous software stacks. You have Java stacks, you have PHP, you have JavaScript, you have Fortran code maybe. We don't have, luckily. And you would need to do all the service mesh functionality for each language again and again. And with a service mesh, when solving that on the infrastructure level, it's completely agnostic from the language. It just works, at least for the base functionality. And what we did is trying that first with Istio. Yesterday, I was in the intro session to Linkerd, and there was one Twitter post on a slide, and that said, if you want to go for service mesh, use Linkerd first, because then you already have a basis, and then you can go for Istio and try that for 9 months. We will see in a second if it took 9 months for us or not. We still started with Istio. So how would that work in a service mesh? As you see here, you have 3 pods which have their services A, B, and C, and each of them have just a proxy attached. And usually you would have another client within the cluster which has its own proxy. It interacts by using the proxy transparently. You don't need to do that yourself in the application. It interacts with the service A in pod 1, and then your request just gets forwarded through your different pods. And if you have a destination in the end, then that destination within the cluster is still attached to a proxy. But what if your client application or your destination application is not part of your Kubernetes cluster? Then Istio has something like an ingress gateway and an egress gateway. So you have a client which is not service mesh or not Istio aware outside of your Kubernetes cluster. Requests from that client would be ingested in an ingress gateway, like an ingress controller in standard Kubernetes. And that has its first instance of a proxy, and every proxy-to-proxy connection then has the full flexibility and the full capabilities of the service mesh, like, for example, the TLS encryption between the proxy and the ingress gateway, and the proxy of pod 1 would already be handled by Istio. The egress gateway is an optional component. You don't need to do that. You can directly connect to the outside world without the egress gateway as well. But the egress gateway can provide additional functionality if you have a dedicated host which has maybe a dedicated IP address, and only that one is, from a firewall perspective, allowed to connect to the outside world out of the Kubernetes cluster. I promised I will show you a bit of YAML how Istio would be configured, not the Istio control plane itself, but just for a given service. What you see here is you have a client pod and a virtual service and a destination rule. These are 2 CRDs for Istio, and then the request would go to the destination pod. And what you need to do for a Istio service is you need to configure a so-called virtual service. The virtual service has, in this case, an HTTP service. It has a route definition and says 75% of the requests for the review service go to version 1, and 25% of the requests just go to version 2. So what is subset V1 and subset V2? This is defined in the destination rule. There you have the subset declaration and say subset V1 is made up of all the pods which have just this label combination. So the pods need to have a label version V1, and then it's part of subset V1. So that's already it. For each subset, or generally, you can provide a dedicated load balancer specification, so if you want to distinguish between random robin or round robin.
Okay. So how do we connect all that to the old world with the bunches of legacy applications? That's what the mesh expansion of Istio can do. And what we work mostly with is the mesh expansion that has been offered in version 1.0. And the principle is relatively easy. You just install the Envoy proxy at the side of your application on the virtual machine or physical host, and just connect that simply to the control plane of Istio, which still resides on the Kubernetes cluster. As Stephan mentioned, TLS encryption, mutual TLS encryption was the main focus because some of the applications are not, especially the internal ones, are not totally capable of running TLS by themselves. So that was very, very important, and getting client-side authentication is very important to replace that ACL stuff. In particular, in the service mesh, we can declaratively connect things and thus replace the ACLs. And this instantly also gives you all the telemetry and observability, circuit breaking stuff, and all the features that Istio just brings with the proxy. And this is how it essentially looks like. I just explained it's essentially installing the proxy on the hosts, connected to the control plane. And what immediately worked was calling host-based services from the Kubernetes cluster. This is what the arrows indicate. But the same task is true for the other direction, which turned out to be a little bit more complicated, calling cluster services from within hosts.
So, but mainly we are here because of the problems we had when using Istio, at least in our setup. I will not say that it's not our fault. I'm sure quite of delays have been our fault, maybe not using most priority on that. But we are here to show what we stumbled upon. First thing we noticed are security concerns. I mentioned we run in a multi-tenancy environment, and the multi-tenancy environment has pod security policies. So usually we don't allow pods running as root, and usually we don't allow pods writing in their topmost container layer. If they want to write something, they should mount volumes. So the Istio control plane doesn't do that mostly. Okay, the control plane components, we can say, hey, that's managed objects from us as a cluster provider, that's fine. But in Istio 1.0 and before, in fact, before Istio CNI existed, the proxies for each application come into play by being a sidecar container in your application pods. And these sidecar containers are enriched either in an automatic fashion or in a manual fashion. Manual fashion means you have an Istio control command line tool which enriches your Kubernetes manifest, and then you can do a kubectl apply and send them to the cluster. The sidecar container, the proxy sidecar, or no, in fact, not really the proxy sidecar, the init container which changes your IP tables rules. This needs privileged mode, and it needs netadmin capabilities. And since that's done as part of an application deployment, these are privileges an application operator needs to have, and not the cluster operator. And this is something we really did not like. And that was a problem for us. The same problem was with the book info sample application of Istio. They want to run as root as well in most places. I think this has improved in 1.1, but still not at the end. But we have some patches which we would like to submit to get that fixed. As well, the sidecar injection, that's the automatic mechanism I mentioned. You can just inject your manifest into a tagged namespace, and then an admission controller will enrich your configuration. If you use pod security policies, you get a problem with the order of events. Partially, your admission controller for Istio enriches the pod before the pod security policies are evaluated, or vice versa. And it might have happened that you had the wrong pod security policy identified automatically, and then the sidecar was attached, and then the deployment controller could not deploy your pod anymore because it needed too much permissions for the currently active pod security policy. Another problem we had with the mesh expansion was the connection to the control plane. In Istio 1.0, we had the problem that an expansion node needs to have DNS tweaks. You need to tell him that a cluster internal name is available at the IP address of the ingress gateway of Istio. There was no way outside of the world to bring that into DNS. So the first thing was, and that was part of the documentation of Istio, that you install a DNS mask on your expansion nodes and then inject your DNS configuration there. Even when we had that, we could not submit telemetry data to Istio because that was just done as part of the Istio proxies, and it tried to reach a pod IP address and not a configurable gateway IP address. And as I said, our pod IP addresses are from the CGNAT range, and they are not routable, so we were not able to submit telemetry data. And the inbound part, so you have a host-based installation outside of the cluster and want to call a Kubernetes service with mesh expansion, that we didn't get running at all because it wanted to contact the pod IP addresses of the destination service as well. And MTLS did not work out of the box as well.
Okay, so in the end it turned out that Istio 1.0 was not essentially suitable for our problem and our use case to run. It was too many things we had to tweak, too many things that didn't work smoothly. And in particular, Stephan explained, the expansion didn't work as good as we needed that. So that was actually a blocker of migrating lots of services into the Kubernetes cluster, because in that case they wouldn't be able to reach their dependencies. So we needed an intermediate solution for helping our colleagues to migrate their stuff. What we did as an intermediate thing was something we internally call the service mesh lite. Don't take photos of that, please. It's all online. So we mimicked a setup that looks a little like a service mesh, but it isn't. In the Kubernetes world, we put a square sidecar container in front of that to unload client certificates and TLS. On the host sides, we put an Apache, which in most cases we already have available, to unload the TLS encryption and verify the client certificates. We could sort of semi-automate all of that, and that helped a lot of colleagues to proceed with their Kubernetes migration. But of course, that's not the thing we want to do in the long run.
So, Istio 1.1 has been released. Istio 1.1 to the rescue? Spoiler, it got a lot better. The control plane connections, yes, we got them running with Istio 1.1 without a problem. Outbound expansion, so I have a Kubernetes service and want to talk to some host-based installation outside of Kubernetes. Works like a charm. MTLS setup, yes, MTLS as well, or both, between Kubernetes servers and expansion servers, and for the control plane components. Yes, works out of the box. And the one thing I mentioned with the IP tables configuration, Istio CNI is out, runs with admin privileges as a CNI plugin, and not with operator or application operator permissions anymore. So even our security concerns there have been solved with Istio 1.1. But there always is a but. Inbound expansion, still not working so far because it tries to reach pod IP addresses directly. The automatic sidecar injection, the thing with the order and pod security policies, we did not test that successfully with 1.1 as well. The documentation and generally service mesh or Istio, it's complex. It's not something you should just take on lightly. It's absolutely doable, or I hope at least, but it is complex, and the documentation is partially, but that's a matter of development for a fast-running thing, the documentation is partially inconsistent. And one thing which is very important for us, multi-tenancy, that's a bit unclear still. who is responsible for deploying which artifacts into the cluster. Like, who is doing the virtual service? Who is doing the destination rules? Is it the destination service provider? Is it the client who wants to deploy that thing? And do other things come up which are unclear? Who has to deploy these services and who needs to have the permissions to deploy specific CRDs? What's up next? Of course, solving the remaining issues to have a final picture on if Istio is the right choice for us to use. We want to get the inbound mesh expansion running. We need to evaluate that in large scale. There have been multiple discussions regarding the performance overhead of service mesh. We want to test that with our test setup. We do have services which have thousands of requests per second, so that most likely those services will not be one of the first candidates to do. Yeah, that's part of the production readiness things. Redundancy needs to be tested that it works properly. We need to tune the permissions of the control plane components and of the CRDs. That goes again into the multi-tenancy thing. And yeah, performance and overhead I already mentioned. And we can get more benefits out of Istio, especially Istio 1.1 and further. Multi-cluster connectivity, that's definitely a topic for us. We want to connect, for example, our front-end and back-end clusters, or make it available that we connect one cluster of one data center with the corresponding cluster in the other data center to help with failover, to have an in-mesh failover. The locality-based routing goes into the direction as well. We want to have the shortest possible data paths. So why switch over to the other data center if there's a locally deployed service, maybe even rec local? SPIFFE interoperability. Currently, we plan for multi-cluster with just having a certificate of the same root CA. But we want to have general interoperability by using the SPIFFE standard, and Istio has support for that. Error scenarios are to be tested anyway, and authorization is as well something we did not look into so far. So specific request-based authorization, we just have the service-to-service interaction covered so far. And Istio was our first choice, but we definitely will evaluate Linkerd as well, Linkerd 2, in fact, and we will see how that behaves according to our requirements. And I mentioned that in the beginning, I think we definitely want to provide upstream patches for our concerns as well as far as we can patch them.
Okay, so in summary, I can probably say that it looks like Istio 1.1 fits what we need. Most of the things look fine, in particular compared to 1.0. A couple of things need to be clarified, but yeah, it's doable, we think. As you heard, it's not too easy to set it up, and a couple of organizational questions need to be clarified. But the overall summary is that the direction of development in Istio 1.1 is very, very promising, and I suppose that at the latest with 1.2, we are fully able to set sails and speed up our cloud-native journey. Thanks.